Hey everyone, this is my first part of the first chapter of the talk series, which is on machine learning, and I'll be taking help of this book, which is a pretty great book because it contains moderate amount of mathematics, but a good amount of like example and codes so that you can get your hands on very easily. So today's topic is singular value decomposition, and I think most of you are already familiar with it. Uh, and it's the part one. In the second part, we'll be discussing PCA modes, that is principal component analysis. We can talk about it afterwards. So, okay. So this is going to be the roadmap of today's talk. So first of all, we are going to ask the question why we use SVD in most of the data-driven methods. So data-driven methods are the methods in which we try to predict and learn a system using the finite data we have or the finite snapshots. The data can be in the form of anything, but mostly we create matrices out of it because it is finite data and we know the matrix theory. Then we'll see the definition of SVD and what is economy SVD. Then we'll go through some application like matrix approximation, and one of the cool direct application of SVD is image compression. So we're going to just go into the code and see how actually it can highly compress a good resolution picture and recover most of its components in very few modes. Then we'll see some of the mathematical property or just the idea how the correlation matrices works in this case. And at last we'll see how SVD is used to find the pseudo inverse of non-square matrices, and we'll work with least square and regression, and this is how it is directly connected to almost all the machine learning problems we deal today in our real lives. Okay, let's go. So why SVD? So many complex systems may be linear or nonlinear. They can generate data, or they have the data which can be arranged as a matrix or an array. So if you, can I use one of the marker? So if you have an image, say image X, so your matrix can be the pixel values, and this data can be stored as a matrix. And if you have a movie, so you can take like snapshots at particular time interval. Say I have taken the snapshots at 5 intervals, and for each photograph I can arrange them as arrange the pixel of those photographs as columns, and again my data will be in a matrix form. So in most of the cases we can actually arrange our data in the matrix, and if we know how to deal with matrix and how to extract most out of one matrix, we're good to go. So, and the second point is these big matrices usually have coherent low dimensional subspaces which can very well define the behavior of the whole matrix. And this is exactly what SVD does. SVD, or singular value decomposition, extract those latent important components out of a big matrix so that we can represent our data in a very compact form comparatively. So yeah. So what type of data we have? We have already discussed. Like most of the real world problems, we have data and we can arrange that data in the form of matrix. And the most common case, in the case of matrix also, we have this skinny tall matrix, because In this case as well, every picture will have 1000 of 1000 and multiply by thousands of pixels, but we'll have, say, at most like 500 to 1000 snapshots. So in the usual case, we have these kind of skinny, tall matrices, but it works with other metrics as well. But this is the most case we see. So what's the definition of the SVD? For any matrix, there exist unitary matrices U and V and a diagonal matrix, so that I can represent my original matrix in this form. U and V are unitary, and the columns of U are called left singular vectors. Columns of V are called right singular vectors, and the diagonal entries are called singular values. These are very much related with the eigenvalues and very comparative, but the best part is this. The representation of singular value decomposition comes with the hierarchy. So the most important singular value comes first, and it decreases in values. So this is important. What economy SVD is. So in the particular case, if we have n greater than or equals to m, our diagonal matrix look like something like this. So if we just truncate the part of the U matrix we are not needing, because it will be multiplied by a 0, we get our economy SVD, which is much smaller representation. This is economy SVD. Now talk about the existence. So one of the good thing to work with SVD is its existence. It exists for all the matrices. So I know there are two proofs we can go with. One is in the linear algebra done right. It's for the matrices, and it's simple and direct. The other is that every compact operator has a singular value decomposition. It's not a hard proof either. All you do is, so if you have a matrix, you find these two correlation matrices, and after computation you get to know that these are self-adjoint matrices, and on the self-adjoint matrices we can apply the spectral theorem. So if you want, I can show you a good video on it. You guys can go through the. Oh, where is it? Singular value decomposition. So this video is by Joel Rosenfeld, the professor I'm working with, and he gives a very simple proof of how SVD exists for all the compact operators, and matrices are compact operators. So you can go through this video. It's fun. So we're good. We have a matrix, we have our data, and we arranged it in a matrix, and the SVD always exists. So first question is, how do we calculate SVD? So I'll just go through my code window. I'll just show you. It's just a simple code. Where is it? Yeah. So do I need to? Yeah. So we are just importing the library that we need for the mathematical operations. We assign X to be any matrix of our choice, and assign random numbers to it. And these print commands are like optional, but what we actually do is we assign U and the diagonal matrix and the V matrix, and we just command it to calculate the SVD, and we get the SVD. So I have so you can see this is our U matrix, and we got our diagonal matrix as well, and the V conjugate transpose matrix as well. So it's this easy to find SVD. And in most of the algorithms in machine learning, or the thing we do, like system identification, this is one of the most basic part, and then this SVD is used for the greater cause. So it's for the economy. Okay. So they don't want the zero values in the diagonal matrix. So they said that they do not want the diagonal matrix, zero values of diagonal matrix.
I guess if there were a zero,
yeah, yeah, yeah.
But, okay,
so where were we? So let's see how do we actually approximate matrix. So if we have a matrix X, what we can do is we can apply SVD, and since our sigma matrix is a diagonal matrix, we can write X as a sum, and with our choice we can truncate this sum the way we want to, the amount of information we need. So, and the good thing, as I told you guys earlier, this singular value is the most important one, and the second one will be the comparatively less, and this will be the least important. So we don't have to worry while truncating that we will be missing out some like principal component of the data. So this is how we actually find the R rank approximation. So we just keep the R sum terms, and then we truncate the other things.
So your singular values you've ordered them in decreasing order?
Yeah. Okay. Yeah. And we have a nice theorem called Eckart-Young theorem, which says that the R rank approximation of the matrix, of any matrix, is the best approximation if it is a truncated SVD. So if you are using SVD for R rank approximation of any matrix, in the L2 or Frobenius norm sense, this is the best approximation. So that is the reason we use SVD, because it always exists and it is the best approximation in the L2 or Frobenius norm.
Is there something about the technology or the data that suggests that the Frobenius norm, or the L2 norm rather, is the correct one to use, or is it just a choice that you can make?
It is a choice, because sometimes what happens is, like if you have like if you have a problem, and if you have like data points something like this, and you want to do the regression, say your least square will find you approximation something like this, but if you are using soup norm or something, it may find something different, but we are never sure which is the optimal norm to use. Like we can use L1 or L infinity.
But there's nothing about the situation that makes it obvious why one norm would be a better choice than another.
No, because we just have in machine learning we just have finite data, and we cannot say which prediction is the best prediction.
So one thing that's nice about the L2 norm is computationally efficiency. That's really nice, because you're just squaring, you're just writing some new mod. So if you wanted to take a P norm, for example, this would be computationally much more expensive.
Yeah.
Okay.
That's more practical as opposed
Yeah.
to like something that's given to you by the program.
Right, right.
So we have the Icart-Young theorem, which is we are going everything
So can I
great.
ask this theorem? It's very nice. How old is it? Is it a year?
I don't know. It's pretty old, but
I'm just curious.
yeah, I wanted to look into the proof, but I didn't get the time. But I'll definitely look into the proof because it somehow like creates a least upper bound or the lower bound for this norm, and the proof must be something beautiful. I will definitely look into it.
Probably an orthogonal
Ye-
regression proof.
yeah, maybe. Okay. A cool application will be image compression. So let's go on to the code again. This is good. Okay. So this is a picture of a dog and picture of a cute dog, and this is our data. So basically what we have done is A was the image, we turned it to a grayscale, and we arranged the pixel in a matrix. So basically X is a matrix which is a picture. So if you want, if we can like, if you want, we can see the actual size of the image right now. So it's 2000 by 150. So it's a pretty big matrix right now. But the quality of the picture is good as well, so it's okay. But if we want to compress this image and keep the most of the high definition and the details things, we're going to try SVD. So first of all, this is our data, and let's try its SVD. So this is the code for SVD. So we assign the matrices and we calculate the SVD here. And this part of the code is for the truncation, the matrix approximation truncation. So for different values of R, we'll get different results. So for instance, if I just take the first 5 component or first 5 values, singular values, and try to run this code. So even for just 5, we start to get idea how this picture might look like, right? And yeah. Yeah. And for 20, we can say that it's not a dinosaur. And if you put R equals to say 100 first. So we are taking first 100.
So the original size was
2001, yeah.
okay.
So and we are taking just 100 first 100 singular values for the approximation, and this is the picture we get.
Is there, I notice on the less resolved images, we see a lot of these artifacts that are like in the form of like vertical and horizontal
Yeah.
spreadings. Is that somehow connected? Like
Yeah,
okay,
yeah.
all right.
So they are connected on. So my matrix is this, right? So, oh, this is B. So you can use your intuition as this is responsible for the vertical lines, and this is responsible for the horizontal line, or vice versa. It depends on the data. But horizontal or vertical, and this guy scales them. So this is how we actually create the most of the information that we have in the matrix.
And so that would kind of give you the intuitive understanding. And I suppose that it does entirely follow from like you're arranging that you have a matrix that's representing this image, and again, like the vertical and horizontal rows of it
Yeah,
are
yeah.
in fact corresponding to the
Yeah,
vertical and horizontal
exactly.
rows of it.
Yeah. So the 100th rank result is pretty good. And if you see, if I go from 100 to 200, it doesn't make much of a difference. So what we can like confirm that is after using a good number of singular values, then most of the data does not contribute that much, right? Yeah. So this is the plot for the singular values, the value of the singular value. So you can see that from 0 to say 100 or 150, we got most significant values, and then they started to decrease. They started to, yeah.
Just a minute here. You're going down sigma, which has essentially a diagonal. So have you gone down 200, the first 200 entries? Okay, so that's good
Yeah.
enough to get
Yeah.
the dog that you can post on Facebook.
Yeah.
Okay, just want to be sure that answers came up.
So yeah, as we can see, from 0 to say 150, we get most of the significant values that we want to use in our data. And the other are, we just, if we want to and we want to save our memory and data, we can like just truncate the rest of the stuff. Yeah.
So if you pick 100 and 200,
Mhm.
values are, and you get a good picture, is there in general a rule of thumb where like if we pick 10% of the biggest singular values, we'll get a good picture?
That totally depends on the data you have, the data you are dealing with. So
It's like
not all the data give away everything in the few.
it depends on
Yeah.
how much entropy it has, kind of like.
Yeah. That. Yeah. Exactly. How much spread out your data is.
Yeah, you could probably curve fit
Yeah.
like this and then do some calculus and try to figure out
Yeah.
where it's
So
changing most or
yeah.
where the
So if the value of your singular value is not decreasing at that rate, you'll be you should like use more of the values, like higher rank. And if it is something like this, we already know that I can just uh, like truncate after a while. And this is the cumulative sum, which is the R rank approximation. And there also we can see after say 200, it's almost constant. So the other terms are not as much contributing to the sum or the data. So this was image compressibility. Okay, good.
Nikhil, just to make sure, can you see an orange light on that?
No, I was seeing it, but not now.
Okay, well, I think this
Yeah.
iPad's still picking up, so
Okay.
Mhm.
I'll just get up.
So this was image compression. So we'll see the intuition that we were talking about, how it connects mathematically. So SVD, and even in the proof I show the video of, contains this part. So SVD is tightly related to these two matrices. These are the correlations that find out how columns and how rows are correlated with each other. And if we substitute SVD, economy SVD in these two correlation matrices, we get the singular values are nothing but square root of eigenvalues of these two correlation matrices. So we are actually finding the the eigenvalues of the correlation matrices, and this is included in the proof as well. So since the singular value solves these two eigenvalue problems, singular vectors, sorry, the best interpretation we can take is U in the singular decomposition captures the dominant correlation in feature space, that is the rows, right? And V captures the dominant correlation in time samples, like how our data is changing with each snapshot, how each snapshot is like changing with time. Okay. So eigen SVD can be seen as a generalization of eigen decomposition, because we, for the eigen decomposition, we find the eigenvalue and eigenvector, and but for if your matrix is Hermitian or self-adjoint, that can be written as V and the eigenvalue matrix and the V star, which is very much related to the singular value decomposition only. This is one of the important property that SVD is invariant under unitary transforms. So if you apply unitary transform to SVD, it will be same as that of the original matrix. DFT, which is discrete Fourier transform, is an unitary transformation, and SVD of X and SVD of the singular value decomposition of X gives you the same answers. And the only difference is, if you are doing the operation from the right, it will be F will become FU. It somehow just rotates the matrices, and so, and if you are applying your unitary transform from the left, it will be U and V, sorry, yeah, transform by the inverse, yeah. And the last part of this talk is pseudo inverse, least square, and regression. So most of the physical systems we represent in machine learning problems can be written as Ax equals to B, where A is known, X is unknown, and B is known. So we tend to find what the value, what the vector X is. So if our matrix A is like square and invertible, we do not have any problem. But in most of the real world problem, they are not square matrices, and the system is overdetermined or underdetermined. So we want to find a way so that we can find the inverse of non-square matrices. This is where Moore-Penrose inverse comes to the picture, and it's just an application of singular value decomposition. We use singular decomposition to make a non-square matrix a square matrix, capturing the dominant patterns, and then we take the inverse of it. And again, this zero inverse will be the best fit to find the vector X under 2 norm. So we'll see 2 examples in the coding of linear regression and multilinear regression. Let's see. uh, this is the first example, and the problem is a x equals to b, and we want to find what the value of x is. So the x, the value of real x is 3, and but b is noisy. So whenever we record any data in real world problems, the data comes with a noise, and we want to still find the best fit so that x should something look like 3, right? So what we will do is we will find x as, it's denoted by a dagger, this is pseudo inverse and b, right? So this is the easiest example we can find for regression. So this is exactly what they have done. Find the x tilde, which is the approximation, and this is the plot we got. So the true line for x equals to 3 was the black one, and this b was the data points, and the data points were noisy. So, but still, we got a good prediction using the SVD and using the pseudo inverse mechanism, and so somehow SVD can also be used as a noise reduction tool, because our data had the noise reduction, but we find the best fit out of the noisy data, and this is it.
So I'm confused about what you mean by x equals 3.
So it's basically the slope of the line.
Okay.
Yeah.
Like, given the data, what's the actual slope versus what's the slope you can estimate given the finite number of data points?
And for the multilinear, yeah.
The terminology noisy.
Mm-hmm. Oh, noisy.
Yeah.
So it's just the unwanted data values we have, or the errors. Say, if your real matrix should look like, say, 2, 3, and 7, and but you record this data in, say, in and with using your mic, which is not of very good quality. So this data will be something like 2.7, 3.1, or 6.8. So this is a noisy data. And we can add different type of noise in most.
So that means there might be another terminology for that noise.
Sorry?
There might be another terminology for this word noisy.
Yeah.
So do you find
Especially,
the
yeah,
terminology?
when you're storing data or
Yeah.
measurements or stuff like that, it's called noise.
Yeah. Even if you record a sound, and if you are intended to record sound of a bird, you will place the mic around birds, but there will be sound of like traffic and the other people as well, and some like vehicles and stuff. But you will try to cancel out that stuff and just focus on the data that you want. That is the denoising of the data. And this is the same, but a little bit more. Yeah, this is multilinear. This is the example for a multilinear regression, where my A matrix is not a vector, but it's a non-square matrix. And we will be solving this with the same algorithm we will find the SVD of A, and this will be the approximation. Yeah, this will be the approximation of the X. And as you can see, the black one was our data, y-axis is the heat produced, and the x-axis is the number of experiment. So the black lines are the actual data, and the other one is the result of regression. Yeah, it's not that good, but it depends on how much data we have and how rich is the data. So if we have like a small matrix and less number of snapshots, we'll not be able to capture everything, but it tries its best to find the good fit for the model. I think these are some conclusions. So basically, SVD is just not a decomposition, is a data adaptive coordinative system. So it reads the data and then form a new coordinate systems that allows us to get most of the information in like finite rank or the less rank. And the other thing is low rank is everywhere. Most of the data we deal with in system identification or machine learning problems can be decomposed or can be approximated by lower rank matrices. Icard-Young theorem is important because it gives the guarantee that the pseudo-inverse we calculate using the SVD is the best fit. It is numerically stable, and so in most of the machine learning problems we tend to learn the dynamics or learn the model, and this is the one of the most basic part we do is to regress the problem. We know the x values and we know the y values. We want to find the operator or the function. We just do the pseudo inverse, and that's how modern machine learning works right now. And that's it. Thank you. Yeah.
Is there an analog of this discussion on Eckhart-Young for tensors?
Yeah, there is. In the next part of the talk, I'll be discussing the SVD on tensors as well. So, yeah, we can talk about it. Like if we have actual proof of the theorem for the tensors as well or not. Yeah, but we do have SVD for tensors and higher dimensional things. Yeah.
Apologies if you said it while I had stepped out for a minute, but did you give any explanation or even a sketch as to why the SVD method is particularly robust against errors? You mentioned it was numerically stable, so
Mm-hmm.
any general principle or reason why it doesn't see errors very well? Or?
So you mean the noise, right?
Yes.
Yeah. So if we have any, say, noisy data, and we are finding the best fit, right? So the best fit will be this. Even if the data is noisy, but we can hope that most of the points will on the line as well, because we have a rich data, right? So if we are finding best fit for the data, then we somehow are denoising the whole system. That is the reason we are saying that it is like it can be used as a denoising tool. We
Sort of a philosophical question, right? Like noise ends up like jumping out of place, and the best way to calculate it seems to be just the distance that it travels
Yeah.
over space time. So that's why alpha norm kind of sorts things out.
Yeah, like what we are doing there is just trying to minimize the sum of the square of the distances. So if we have like noise and we will be like finding to be particularly away from the noisy points.
Yeah, and
So
it will, because we're squaring, will also
Ye-
give higher weight to the things that are further outlying.
exactly, yeah.
All right, thank you.
Um, Next talk will be for the SVD2, where we will be discussing PCA, which is like the other name for SVD, but it uses more statistics to like define or to approximate data in a more statistically better way. And we'll also have a look onto POD, which is principal component analysis. That is PCA, sorry. Principal orthogonal decomposition. And then we'll be seeing the SVD for vectors. Then this topic will be closed. Then we can move to the next chapter.